Think about your morning routine for a second. The alarm goes off, you flip on a light, you check your charging phone, maybe turn on the coffee maker. Electricity literally powers absolutely everything we do, yet it's a completely invisible force. Well, welcome to this explainer. Today, we're going to unlock the mystery of electricity. We'll be taking a structured journey into the fundamental properties of circuits, turning those invisible electrons into tangible rules you can actually visualize and understand.
Okay, let's dive into this. Here is our roadmap for today. First, the flow of electricity. Second, the rules of resistance. Third, Kirchhoff's circuit laws. Fourth, comparing series and parallel resistors. And finally, putting it all together with circuit analysis.
Section 1. The flow of electricity, from invisible electrons to tangible power.
All right, before we can mathematically analyze a circuit, we really need to understand what is physically flowing through the wires. Let me ask you a question to make this abstract concept a bit more tangible. When you think of a power source, you probably picture a heavy battery, or maybe a massive hydroelectric power plant. But how much current do you think an everyday ordinary household lemon can produce? It sounds a bit like a middle school science fair project, right? But it actually perfectly illustrates the core physical reality of electrical current.
So check this out. We've got a zinc strip and a copper strip inserted directly into a lemon, and they're connected by wires to an ammeter to measure the current. The common acids inside the fruit act as what we call an electrolyte, which is really just a conducting solution. This setup frees up the outer electrons in the atoms of the metal strips. And because these outer electrons aren't tightly held to their nuclei, they become free electrons and they start to move. That physical movement of free electrons through a conductor, that is exactly what electricity is. It's literally a physical moving flow.
Let's define this a bit more formally, though. Direct current, or DC, is the continuous flow of electrons in only one direction through a circuit. They flow from the negative terminal of the source, so like our lemon or a standard battery, and they travel through the conducting wires straight toward the positive terminal. Now, what is truly mind-boggling here is the sheer scale of this flow. When we measure electric current, we use a unit called the ampere, named after the French physicist André-Marie Ampère. Just one single ampere of current means over 6 billion electrons, that's 6.2 times 10 to the 18th power, are moving past a single point on that wire every single second.
To highlight the real-world stakes of that microscopic river, let's look at how the effects of direct current on the human body scale rapidly. Because our human nervous systems operate on very small electrical signals, even tiny fractions of an ampere have a massive physical impact. At just 0.0008 amperes, you just feel a slight tingling, but jump up to 0.075 amperes and you experience severe pain and difficulty breathing. At just half an ampere, it can cause possible heart fibrillation. This shows you exactly why electricians absolutely always turn off the power before working on household circuits.
Moving right along to Section 2, the rules of resistance, adding friction to the flow. Now that we understand the immense flow of current, we need to look at the physical obstacles that slow it down. It's kind of like riding a bike off a smooth road and into thick mud. That mud adds resistance to your movement, right? Well, all matter has some resistance to the flow of electric current. A guy named George Simon Ohm actually figured out this relationship. Ohm's law basically states that the voltage in a conductor is proportional to the current, assuming the temperature remains constant. A really great mnemonic to remember this equation is V equals I times R, which you can think of as very important resistance. V is your electric potential difference or voltage, I is your electric current, and R is your electrical resistance, which we measure in ohms.
Section 3. Kirchhoff's circuit laws. The rules of the road for electricity.
So, Ohm's law gives us a great micro-level view of a single component. But what about the macro rules governing how voltage and current behave across complete, complex electrical networks? Well, meet Gustav Kirchhoff, a pioneering German physicist. Way back in 1845, he investigated circuits and described two incredibly important laws. Today, whether they are controlling a massive provincial power plant or designing the intricate circuit board inside the cell phone in your pocket, engineers literally use the exact rules Kirchhoff discovered to safely and predictably design modern circuits. His brilliant work boils down to two core principles. First is Kirchhoff's voltage law, or KVL. It states that in any complete path in an electric circuit, the total electric potential increase at the source perfectly equals the total electric potential decrease throughout the rest of the circuit. In incredibly simple terms, voltage gains equal voltage drops.
Second is Kirchhoff's current law, or KCL. This states that in a closed circuit, the amount of current entering a junction is exactly equal to the amount of current exiting that junction. Think of it like a river splitting into two streams. The total amount of water doesn't change, it just divides.
Section 4. Series versus parallel resistors, managing the traffic flow.
Now we're going to connect Kirchhoff's macro laws directly to the physical arrangement of resistors in our circuits. To vividly understand how circuit layout changes everything, imagine an amusement park. You've got your ticket, there's a huge lineup, and you just want to get in. So how is electrical resistance exactly like an amusement park turnstile? Well, the flow of people into the park is like our electric current, and the turnstiles represent resistors that physically slow down that flow.
So, the crucial point here is how you arrange those turnstiles. In a series circuit, you add resistors one after another in a single line. Imagine adding another turnstile directly in front of the one you literally just passed through. Everyone has to go through both of them. This creates way more total resistance and slows down the overall flow of current. But in a parallel circuit, you add open turnstiles side by side. Even though each individual turnstile still presents a barrier, adding more of them side by side creates more pathways. So overall, adding resistors in parallel actually results in less total resistance and more overall current flow. It's a real game changer.
And finally, Section 5, putting it all together, circuit analysis. We now have all the tools we need: Ohm's law, Kirchhoff's laws, and our rules for equivalent resistance in series and parallel circuits. Let's see how this builds into a foolproof, four-step process to conquer mixed circuit analysis. Because, real circuits are rarely just series or just parallel. They're almost always a mix. Step 1, divide the circuit into its series and parallel sections. Step 2, focus just on the parallel part and find its equivalent resistance, basically collapsing those side-by-side turnstiles into a single mathematical value. Step 3, literally redraw the simplified circuit, replacing that parallel cluster with one equivalent resistor. And finally, Step 4, solve for the total overall resistance using your series rules. Once you have the total resistance, you can use Ohm's law and Kirchhoff's laws to find literally any missing current or voltage.
We've mastered the fundamental laws of electrical resistance today, but I want to leave you with a rather provocative thought about the future. Right now, when electricity travels from power plants to our homes, some energy is always wasted as thermal energy because of the resistance of the wires. But scientists are working on superconductors. These are special materials that have absolutely zero electrical resistance. Currently, this requires extremely low temperatures, like minus 135 degrees Celsius. But if room temperature superconductors are achieved, how will they completely rewrite the rules of the power grid we literally just learned? Imagine a computer that never needs cooling, or power plant transmission wires that are 100% efficient. The rules we learned today are just the foundation for understanding where the future of energy is headed. Keep questioning how the invisible forces around you really work.